Now, let us look at another question. Something, the flavor is very different from that what we are looking so far. So we want to count the number of positive integers less than or equal to 300 that are divisible by at least 1 of 2 or 3. It's a very simple question. Any of you can do it in a minute, I believe. So just try it yourself. But here is answer. So let us say that x is the number of numbers divisible by 2 and y is the number of numbers divisible by 3. Right? Or x is the set of numbers divisible by 2 and y is the set of numbers divisible by 3. Now, so one way we can do is that, like, okay, there is what is the cardinality of x? Well, since every alternate number is divisible by 2, we have exactly 150 numbers. And similarly, every third number is divisible by 3, there are 100 numbers. Now the problem is that we cannot add x and y to get the total number of numbers divisible by 2 or 3, because there could be numbers which are appearing in both the sets, right? So x and y might have some intersection. So we will be counting those numbers more than once. So to avoid that, we have to discard those numbers which are counted twice. So what are the numbers which are counted twice? Those numbers which are both divisible by 2 and 3. That means they are the numbers divisible by 6. And how many are there? Well, 300 by 6, which is 50. So now we can use this property that since we have the numbers that are divisible by 3, numbers that are divisible by 2 are 100 and 150. Their sum is 100 plus 150, 250, but 50 of them are common, right? They are divisible by both 2 and 3. So this is let's say both divisible by 2 and 3. They are the ones divisible by 6. And therefore, these numbers that we have counted as part of x and as part of y. So this means that we have counted them exactly twice, so we can subtract that. So I will get cardinality of x union y is 150 plus 100 minus 50, which is 200. Now, this is something that all of you know already. Now, can you prove something similar when there are 3 intersecting sets, like let's say A, B, and C, right? So the following theorem is a homework. A, B, C, B finite sets, then cardinality of A union B union C is cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of B intersection C minus cardinality of A intersection C plus cardinality of A intersection B intersection C, because these numbers we had counted 2 times each, but we have subtracted them more than that. So therefore, we want to put them back again. So we cannot subtract more times than the number of times they were actually overcounted. So as a homework, prove the above lemma. Now we are going to prove a much more general formula for this, which is called the principle of inclusion and exclusion. So what does it mean? We are including the numbers that we want to count first, then the numbers that we are overcounting we are excluding by subtracting. Again, we are including the numbers which we have subtracted too many times. Then again, we are putting up the numbers that we have added too many times, etc. So for this, we need the following conventions. So let X be the universe. The universe means that the set where all the elements that we are going to talk about in the other sets are going to come from, right? So everything is appearing in the set X. So A1, A2, etc., A and B, a family of subsets of X. Okay. Now for any subset, let's say I of the index set, right? So because A1, A2, etc. are indexed by 1 to n. So take the index set 1 to n and then take any subset of the index set I. So we define A subscript capital I to be the intersection of all the AIs where the index I is in the set I. Okay. Now, what happens when I is the empty set? Well, by convention, we define A empty set to be the whole set the universe X itself. Of course, in some books where they follow a different convention, but for our purpose, we will use this convention. Where the reason for the convention is kind of clear that when you take intersection of sets, the sizes only decrease. So if you decrease the number of sets that we are intersecting to 0, then you should have more only, right? The maximum possible elements, which is the universe itself. So therefore, we define A empty set to be the universe X. Okay, with this convention, we can define the theorem of principle of inclusion and exclusion. So let A1 to A and be again a family of subsets of X. Then the number of elements of X which lie in none of the subsets AI is given by the summation over all I subset of the set 1 to n, the index set, minus 1 whole raised to cardinality of I, cardinality of A subscript I. Okay. So we are counting the elements which are not in any of the sets A1 to AN. Okay. So we have the universe and we are counting the sets which does not belong to these sets. Now, it can easily be converted into counting the universe because we just take the whole set X and subtract these elements that is in none of the things, then we will get the cardinality of the remaining things. So that is easy. So here is the proof. How are we going to prove this? Okay, so we are going to prove this by counting the elements in the set X, right, which are not part of the AIs, and see what are their contributions to the sum that we are looking at here. So we have a sum here, right? So take every element of X and see what is its contribution. Now, if you can show that in the sum, the contribution of an X which is not in any of the AIs is exactly 1. And for every element that appears in one of the AIs, the contribution is going to be exactly 0. Then the sum should give exactly the number of elements which are not in any of the AIs, right? So we are going to show precisely this by taking each element X and say that what is its contribution. So first we observe that the given sum is a linear combination of the cardinalities of sets AI with coefficients either plus or minus 1. Now, if X, the element X does not belong to any of the sets A1 to AN, then the only term in the sum, right, that we are looking at, where the element X appears, right, it contributes to is the empty set when I is equal to empty. Why is that? Because if I is not empty, then we are looking at cardinalities of AIs, where AI is the intersection of the sets in which this indices the element X is appearing, right? So therefore, X must appear in one of the AIs to be part of any term in the sum where when I is non-empty. So therefore, the only term in which X is not appearing in any of the AIs is when I is equal to the empty set. Now, when I is equal to empty set, what is the contribution? What is the contribution of X when I is equal to empty set, right? The contribution of X is minus 1 whole raised to cardinality of I, which is 0, right? Empty set cardinality is 0. So which is minus 1 raised to 0 is 1. And cardinality of AI, where A empty set is defined to be the whole set X, right? So the elements of X are all contributing 1 to the sum, right? And in particular, the elements which are not part of AIs will contribute exactly 1 to the sum. And since the elements not in AI are not appearing in any of the other terms of the sum, its contribution will be precisely 1, right? So therefore, if X is not in any of the sets AI, then its contribution will be exactly 1 because it is minus 1 whole raised to 0 and cardinality of AI is going to be the cardinality of X. So each element contributes exactly 1. Now we look at the elements which appear in at least one of the AIs, right? So if X is appearing in at least one of the AIs, you consider the set of indices I in which X is appearing, right? So J to be the collection of the indices I such that X is in AI. Now this is a non-empty set because X appears in at least one of the sets. Now X belongs to AI precisely when I is a subset of J, because by definition of J, X is there in AI, then that index is there in J, right? So X belongs to AI precisely when I is a subset of J. So now the contribution of X to the sum, right, is summation over all I subset of J, right, minus 1 whole raised to cardinality of I, cardinality of AI. Now this is for an arbitrary element X, so J can be arbitrary, right? But what is this sum, right? Now, cardinality of AI, what is the cardinality of AI here, right? So, how many times the element X is appearing in so we know instead of we don't know the cardinality of AI, so we are going to count this in a different way, right? So what we are going to do is that for each element X, how many times it is going to appear, right? So X is appearing in as part of every subset of AI, right? Every subset AI of J, right? Now, how many such terms are there? Well, we are looking at all possible subsets of J, right? But in particular, we are looking at the subsets of J with, let's say, a fixed cardinality. Okay? So instead of looking at every subset, I collect all the subsets. I collect all the subsets I which has cardinality exactly, let's say, small I. Okay? So what I am going to do is that I am going to let small I is equal to cardinality of I, and then I will collect, I rearrange the sum with respect to this cardinality of I, right? Now, if I take cardinality of J to be small j, then there are J choose I possible I element subsets of J, right? And each of the subset is going to be contributing to the sum because X is in each of these guys, right? For every subset, X is there, right? Every subset of AI, X is going to be there, including the empty subset, because all the elements are there. So therefore, by rewriting the sum as a sum over all I ranging to 0 to j, where I is the cardinality of the set I notice that, in j choose I possible ways I can have the set I with cardinality small I. So what is the contribution? Well, because it is minus 1 whole raised to cardinality of I, so therefore it is minus 1 whole raised to I. Now this is true for every I ranging from 0 to j, And therefore, the summation can be written as summation I equal to 0 to j choose I into minus 1 whole raised to I. But now if you look at this summation closely, we will see that this summation is nothing but summation I equal to 0 to j choose I minus 1 whole raised to I times 1 raised to j minus or j minus I. Okay, 1 raised to j minus I. Again, just add, right? Times 1 raised to j minus I. Just to, because it is just 1, right? So this is basically a binomial expansion, right? Using the binomial theorem, we see that this is basically the expansion of 1 minus 1 whole raised to j. Right? 1 minus 1 whole raised to j is precisely summation I equal to 0 to j choose I, minus 1 raised to I and 1 raised to j minus I. But 1 minus 1 is 0, therefore this total sum is going to be 0. But this total sum is the contribution of x to the sum, where x is an element of one of the AIs. So any element in one of the AIs contributes exactly 0 to the sum. And as we showed before, every element not in AI contributes exactly 1 to the sum. So therefore, this sum basically counts the number of elements that is not in one of the AIs. So that is the proof. Okay. Now, equivalently, if you want to count the cardinality of the union, right, A1, A2, etc., AN, we can either take x and subtract these elements that are not there, or you can write the formula in a different way, which is summation I subset of 1 to n, I non-empty, because that set we don't want, and then minus 1 whole raised to I minus 1, cardinality of I minus 1, because we are changing the sign, right, and cardinality of I. So this will give you the cardinality of the union A1 to AN. What is the proof? Let x be in exactly k sets AI, where k is greater than 0. The contribution of x to the sum is, let us say, m is equal to summation j is equal to 1 to k minus 1 raised to j minus 1, k choose j, right? Because it appears in exactly k sets, every j element subset of this k set, right, contribute something, and that is going to be minus 1 raised to I cardinality minus 1, so it's minus 1 raised to j minus 1. Now that is the contribution. Now what you do, you multiply both sides by minus 1 and add 1. Okay, so I'll get 1 minus m on the left side, and on the right side I will have a plus 1. That plus 1 can be written as minus 1 raised to let's say 0, right? So therefore I can now make the index from 0, and of course, because I multiplied by minus 1, so minus 1 raised to j minus 1 becomes minus 1 raised to j. So I take the summation again, summation j is equal to 0 to k minus 1 raised to j, k choose j, which is 1 minus 1 whole raised to k, which is again 0, therefore m must be equal to 1. So the contribution of an element that is in one of the AIs is precisely 1. And elements not in AI are not appearing because I is non-empty, right? So therefore, we have the proof. So both are versions of principle of inclusion and exclusion, and you can use either of the formulas as you please. So now we are going to use this to solve a couple of problems. So earlier we were looking at the surjections, right? So the surjections from an n element set to a k element set, how many are there? So the number of surjections from an n element set to a k element set, now I say, is given by summation I is equal to 0 to k minus 1 whole raised to I, k choose I, k minus I whole raised to n. Okay, so this is the formula that we have. So we want to prove this formula. So how will you prove this? Again, if you want, you know what result that you have to use, right? What method that you have to use now, inclusion, exclusion, and can you try to think of a proof of this formula by this. So pause and think about this, and then you can continue. So here I am going to give a proof. So let x be the set of all functions from an n element set 1 to n to the n element set 1 to k. So what is the cardinality of x? It is k raised to n, because every possible functions are there. Every element has like n possibilities, right? So each of the k elements can be mapped from any of the n elements on the previous set. So therefore there is k raised to n such functions. So this is a set of all functions, right? Right. So if you look at the functions, we have k raised to n because we have k possibilities for any of the n elements, right? Yeah, that's what we want to say, right? So every element can be mapped to any of the k. So therefore k raised to n possibility. So this is a set of all functions, but we want the surjections. Now what are surjections? Surjections are those functions where all the elements have a pre-image, right? So every element in the k element set has a pre-image. So to use inclusion exclusion, let us define. So we can do in two different ways. I am going to use the first theorem. So I want to exclude the guys that is not required. So I will define my sets AI to be the sets which are the functions which are not surjections. And then I discard the non-surjective functions, and then I will get the surjections, right? So let me define the set of all functions this way. So take a fixed element of the set 1 to k and say that, okay, let's say I, and say that, okay, I look at all the functions which map from n to 1 to k where I is not in its image. Therefore, it is not a surjection, right? So AI be the small ai be the set of functions f for which I is not in the image of f. Now, f of x can be any of the elements other than I, right? So there are k minus 1 such elements. So therefore, the number of such possible functions which does not map to I is the cardinality of AI, that is k minus 1 whole raised to n. There are k minus 1 elements, so therefore k minus 1 whole raised to n. Now similarly, if let's say AI, right, where I is the capital I, has all the functions where image of f intersection I is empty, then I has cardinality k minus cardinality of I whole raised to n. Because again, if a set of elements are missing, right, some t elements are missing, right, then k minus t elements are available. So the functions can go from this thing to any of the k minus t elements. So therefore, we have k minus cardinality of I whole raised to n. That is a possibility. So we can also observe that I is basically the intersection of all AI, a small I, right, where I ranges, I belongs to the set I. So that is something that you can observe. And therefore, we have all the necessary requirements for applying the principle of inclusion and exclusion. So let us use it. Now, again, a function in X is a surjection if and only if it is not in any of the AIs, because we have now every possible elements that I have taken, right? A1 to 1 to AK contains all of these surjections which miss any of the elements. So therefore, it contains all of them. So by principle of inclusion and exclusion, we have summation I subset of 1 to k minus 1 raised to cardinality of I, k minus cardinality of I whole raised to n, right? Is the number of surjections. Now, if I put small I equal to cardinality of I, there are k choose I sets I of cardinality precisely I, and therefore using this observation, we can rewrite this summation as summation I equal to 0 to k minus 1 whole raised to I, k choose I, and k minus I whole raised to n, because I is the cardinality of large I. And this is precisely what we wanted to prove, right? So summation I equal to 0 to k minus 1 whole raised to I, k choose I into k minus I whole raised to n. That is the number of surjective functions from an n element set to a k element set. A corollary to this result is that summation I equal to 0 to n minus 1 raised to I n choose I n minus I whole raised to n is equal to n factorial. Why is that? Well, because when you are looking at surjections from an n element set to an n element set, right, when k is equal to n, they can be thought of as permutations, right? A set from a surjection from a set to itself. So therefore, the number of permutations is precisely n factorial, and therefore the number of surjections from a set to itself must also be n factorial. And this is the formula for the surjections from a set to itself, and therefore this counts the total number of permutations. Now we will stop with a final application where you look at a more interesting question. So we have a party, and in this party, let's say n persons are attending the party. Okay, so n people are attending. All of them came wearing hats. So everybody came with a hat. Now, when you enter the party hall, you know there is a stand where you can keep your hat. So they keep their hats at the stand. Now, when the party is going on, something happened in a nearby place, and there was some explosion sound. So everybody got scared. So they decided that okay, it's time to go home. So they all decided to run out. So they, while hurrying out, they picked up one hat and put it on their head and went. They did not even stop to look which hat it is. So they picked up hats at random. Now the question is that what is the probability that nobody got their own hat? Right? Everybody got a hat that is different from theirs. So to do this, we can again use principle of inclusion and exclusion, okay, to find this probability. So how do we do that? So what we observe is that, see, a person getting his own his own hat can be thought of as a permutation where an element is fixed. Okay. So a permutation where there is no fixed point means that nobody got their own hat. Such permutations have names, that is called derangement. So a derangement is a permutation where there is no fixed point, that no element is mapped to itself. Now let X be the set of all permutations and AI be the set of permutations that fixes the point I. Right? It's very similar to the previous one, so therefore I am not spending too much time. So let X be the set of permutations and AI the set of permutations fixing the point I. Now, cardinality of AI is n minus 1 factorial because it's a permutation of the n minus 1 set, excluding the one element that we have fixed, right? Because every element can be permuted. This guy has to be going to itself. So therefore, cardinality of AI is n minus 1 factorial. Now, what is cardinality of a big I, where big I is the as a subset of the indices 1 to n? Well, if you decide to fix, let us say, t elements, then the n minus t elements can be permuted. Those t elements cannot be done anything. So therefore, it's n minus cardinality of I factorial. That many permutations are there. So therefore, by principle of inclusion and exclusion, we get the result that summation I subset of 1 to n minus 1 whole raised to cardinality of I n minus cardinality of I factorial. But what is this? Well, summing in terms of the cardinalities of the index set, summation I equal to 0 to n minus 1 raised to I n choose I, because there is n choose I possible ways to select an I element subset, n minus I factorial. Now, if you look at n choose I, it has n minus I factorial appearing below. So therefore, I can cancel that out. And n factorial is common to all. So I can take that out. So that is n factorial into summation I equal to 0 to n minus 1 whole raised to I by I factorial, right? Remaining from the n choose I. So this is the number of derangements. So n factorial into summation I equal to 0 to n minus 1 raised to I by I factorial. But now we want to find the probability, right? So the probability that nobody gets the hat is the total number of derangements by the total number of permutations, which is divided by n factorial. The probability is that summation I equal to 0 to n minus 1 whole raised to I by I factorial. And if you remember your calculus, you will see that as n goes to infinity, this summation converges to 1 by e. Right? So the probability basically keeps, as n increases, it increases and decreases and increases, etc. Right? But eventually it converges to 1 by e. At any point, the difference from 1 by e is close to 1 by n plus 1 factorial. Right? It's at most 1 by n plus 1 factorial. That is something you can verify. So, not a very small probability, right? Okay, so with this, we will wind up the lectures for this week, and see you next week with some more interesting topics.